Okay, hello everybody. New series time. So this series, I'm obviously by myself right now. This is kind of gonna be like a precursor to some stuff that I'm gonna do with my colleague Garrett. We normally record stuff together, but he's busy right now, and is going to be more busy than I need him to be to be able to record these lectures and get through this material. Um, So this is just for a preface. There's some stuff I need to know both from my research and for a visit to a seminar that I'm going to in March that I like kind of know, but that I don't feel like I really know. And so if you are watching this and you have not watched anything on my channel before, this is very informal. This is me learning stuff usually for the first time. I am not very good at this. I wish I were. Um, and yeah, there's going to be some stuff that I get wrong. There's going to be some proofs that I hand wave. Um, and I'm a third year undergrad, so like take everything I say with some very serious grains of salt. That said, if you are trying to study intersection theory, and kind of from the background of only sort of knowing what a line bundle is and kind of needing to get your hands dirty, this is maybe going to be hopefully a good introduction, starting with chapter 12 of Vakil, moving very quickly, not working out everything, but moving very quickly through up to about chapter 18. And then once we get to 18, we're going to switch over to Harrison Eisenbud's book, 3264 and all that. Um, because that's a book on intersection theory, and the first 5 chapters have to do with my research, and the rest of it is, I'm sure, very good because Harrison Eisenbud are legends. So yeah, long story short, I'm going to be posting these as often as I can. I'm trying to get like about 2 hours in every day. I did some watching earlier, um, of some lectures that Professor Harris has online. Um, but yeah, besides that, I'm gonna do the rest right now. You'll also have to forgive me. It's 10 o'clock at night, and I'm doing this alone, so bound to make more mistakes that way. Um, So starting off with Vakil. So we're starting in chapter 12. And I'll go ahead and note that just so I have reference. So this is on dimension, is this whole section, dimension and codimension. So at this point, you know a fair bit about schemes, but there are some fundamental notions you cannot yet define. In particular, you cannot use the phrase smooth surface, as it involves the notions of dimension and smoothness. You may be surprised that we have gotten so far without using these ideas. You may also be disturbed to find that these notions can be subtle, but you should keep in mind that they are all subtle in all parts of mathematics. In this chapter, we will address the first notion, that of dimension of schemes. So this should agree with and generalize our geometric intuition. Although we think of dimension as a basic notion in geometry, it's a slippery concept as it is throughout mathematics. Even in linear algebra, the definition of dimension of a vector space is surprising. The first time you see it, even though it quickly becomes second nature, the definition of dimension for manifolds is equally non-trivial. For example, how do we know there isn't an isomorphism between two-dimensional manifold and a three-dimensional manifold? Your answer will likely use topology, and hence you should not be surprised that the notion of dimension is often quite topological in nature. A caution for those thinking over the complex numbers, our dimensions will be algebraic and hence half that of the real picture. So for example, we will see very shortly that the affine complex line, which you may picture as the complex numbers, has dimension 1, but really dimension 2. I think he meant to say double that of the real picture. So, yeah. Okay. Definition. Dimension. So the dimension of a topological space Um, so let X be topological space. Dim X is the supremum of lengths of chains of closed irreducible subsets. AKA varieties. And yeah. Scholars of the empty set can take the dimension of the empty set to be minus infinity. And then the dimension of a ring, let R be a ring. Dim R is the supremum of the lengths of chains of nested primordials. Lengths chains of nested prime ideals. These two definitions of dimension are sometimes called a Kroll dimension. And then yeah, from this definition we get some easy theorems. So namely, dim spec A is dim A. We must be careful with the notion of dimension for reducible spaces. So if X is equal to, or I guess if Z, a ring or a topological space, it's X union Y, then dim Z is actually the max of dim X, dim Y. This sometimes bothers us, so we try to only talk about irreducible topological spaces, like varieties. We say that a topological space is pure dimensional if each of its irreducible components has the same dimension. So I guess this is a definition. A topological space is pure dimensional. If each of its irreducible components has the same dimension. And then the remark here is that a curve is a pure dimension 1 space. Yeah. Okay, useful theorem is that a scheme has dimension n if and only if it admits an affine cover of subsets of at most dimension n. Yeah. Okay, so examples of this are a Noetherian scheme of dimension 0 has a finite number of points. So that's kind of like our motivating example. Let's see. This is fibers of integral morphisms. So that every non-empty fiber has dimension 0. Okay, I guess, yeah, this is something that I'll state as a theorem. So if pi from x to y is an integral morphism, every non-empty fiber of pi has dimension 0. Okay. Yeah. Okay. And he actually gives the proof sketch. So he says if we assume that y is an affine open of the form spec k, where k is the residue field, we must show that if phi from k to a of spec a is an integral extension, then the dimension of a is 0. And we do this by showing that a is an integral domain and that any non-zero element is invertible in A. That's not bad, actually. Okay. A semi-related theorem is that if pi from spec A to spec B corresponds to an integral extension of rings, then dim spec A is equal to dim spec B. I want to also be very clear because I've linked this YouTube channel in various RU applications, and I probably will for grad school too. The pace that I'm going at here is not the pace that I like learning at. This is a lot of stuff that I've seen in like Hartshorn months ago. What I'm trying to do is get everything down on the page, and then I'm going to work through some of this later, or at least think about it later. And I'm going through this a second time with my friend Garrett soon. And so for that reason, it kind of makes sense to just state these as theorems, give some examples where relevant, do some proof sketches, but this is not like what I consider like thoroughly learning it. So please do not misunderstand that. Let's see. Okay. Um, okay. Responds to a minimal prime. Okay, another theorem. Let X be an affine K scheme. and k over, I guess I have to capitalize capital K. K over little k is an algebraic field extension. Then X has pure dimension n. Then I guess then if X has pure dimension n, then X capital K, which is defined as the fibered product through little k of X with capital K, has pure dimension n. And actually, this is an if and only if. Then X has pure dimension n, if and only if. Okay. So what do we mean here? So we have an affine K scheme X, and then we have an algebraic field extension with K. We defined pure dimension to have, okay, irreducible components of the same size. And so we're saying that if X can be decomposed in some way, and K over K can be decomposed some way, then if X decomposes into pure dimension n, then the fibered product of, so we have xk going into X, going into K, going into little k. We have alpha, we have beta. So then this is all of the pairs factoring through the product of things that agree in K has pure dimension n. And so if X is spec A, then if A is an integral domain, an irreducible component of X sub K corresponds to a minimal prime of A tensor capital K through little k. Yeah, and that makes sense. And then suppose A, okay, that is actually a very long proof. This is good. This is something I'm going to bookmark as may come back to later. Just point blank. I don't think this is going to show up for the stuff that I'm trying to get to as like a super important thing to have worked through. Yeah. Okay, so codimension. So because dimension behaves oddly for disjoint unions, we need some care when defining codimension and using the phrase. For example, if y is a closed subset of x, we might define the codimension to be the dimension of x minus the dimension of y, but this behaves badly. For example, if x is the disjoint union of a point y and a curve z, then the codimension is going to be 1, but this has nothing to do with the local behavior of x near y. So a better definition is as follows. In order to avoid excessive pathology, we define the codimension of y in X only when y is irreducible. So let y contained in X be irreducible. Then the codimension codim y is the sup of the lengths of increasing chains of irreducible closed subsets starting with Y closure. So in particular, the codimension of a point is the codimension of its closure. So codim of a point is defined as the codimension of the closure of the point. Okay, we say, I guess this is an irreducible, this is a topological space. And then let P be a prime ideal of R. Then we define codim P to the sup of the lengths of decreasing prime ideals starting at P index at 0. Just as a remark, the codimension of P in a ring A is the dimension of the localization of P. And this is called the height. This is something we've seen in Hartshorn. Okay, so then, yeah. Theorem. So let y contain X be irreducible and closed as a scheme. And then let eta and y be the generic point. Then the codimension of y is the dimension of the local ring at eta. Maybe it's worth making this blue. Okay. Um, yeah, so proof sketch for this, just sketching through kind of like why this works, right? And I think that's kind of a healthy way to approach it with the speed that we're going at, is like when we write down a theorem, we shouldn't move past it without understanding why it works or why we don't need it. And if I can't come up with either, then usually we'll prove it, right? Formally that is. So proof sketch, we know that the closure of eta is equal to y, and so then the codimension of the closure of eta is as defined here. Um, this is equal to the codimension of a point. Right. I guess that's more for topological spaces, so maybe not. Um, hmm. Dimension of a local ring. Dimension of a local ring. Um, hmm. Hmm. Is the dimension of local ring at the generic point? Hmm. Well, according to Google, this is 0. Um, I'm. Hmm. Yeah. Oh, it's the height of eta, right? And that makes sense. And that is exactly what we said. It's the height of the. But then this is the height is the dimension of AP. What is A? A is going to be box. And that actually is the full proof. Okay. So cool on that. Um, okay. Let's see. Yeah, so notice that y is codimension 0 in x if it's an irreducible component of x. Yeah. So remark, if y is irreducible in X, then codimension y is 0. If it's reducible in X, then it's codimension 1. It's the height of the ideal. Yeah, and so then a closed subset, all of whose irreducible components are codimension 1 in the ambient space is a hypersurface. Okay. So then, as an additional theorem, if y contained in X is irreducible closed, then the codimension of y in X plus the dimension of y is less than or equal to the dimension of X. And yeah, I can't. Oh, if X and Y are irreducible varieties, this is an equality. But if X is maybe reducible, it's not. And that actually makes sense. So I think that's a very reasonable thing to say. So less than if, and only if X is reducible. Yeah. Okay. Then just as a fact, in unique factorization domains, codimension 1 prime ideals are principal. And this will be important for divisors. Codimension 1 is rather special. This theme will continue. Yeah. Okay. Local rings of dimension 0. Dimension 0 objects aren't just points. They have further information. Okay, useful proposition. All right, so let A with maximal ideal M be an Noetherian local ring. Then the dimension of A is 0 if and only if M is the null radical of A, if and only if there exists n greater than 1 with m to the n equal to 0, if and only if A has finite length, if and only if, and then every descending sequence of ideals, every descending sequence of ideals stabilizes. Such a ring is Artinian. Okay. So I'm just going to flip through this next section. So this next section is dimension, transcendence, degree, and Noetherian normalization. I'm not sure how much of this we entirely need. And I really don't want to waste time because I am going to do this twice, and so I'm kind of doing this for selfish reasons. And I'm mostly recording this as motivation to focus. So, um, yeah, transcendence degree. And then we got a dimension is additive. Yeah, I don't think we need that. Codimension is the difference of dimensions for irreducible varieties. Okay. Yeah, this is maybe where we'll pick up. Yeah. Okay, so theorem, if well, actually no. I'll just write it as it's written. Codimension is the difference of dimensions for irreducible varieties. And so this is kind of like the big theorem of 12.2, but really the theorem that we're going to spend time on is this. So suppose X is a pure dimensional K-scheme um, locally of finite type. So like a K variety that's irreducible. Let Y contained in X be irreducible closed, and then eta generic of Y. Then dim Y plus dim local ring at eta is equal to dim X. And then this is where we get the actual theorem here. This as a corollary, so I'll actually go ahead and write that here as dim y plus the x codimension of y is equal to dim x. Okay, yeah. So that's important. This just kind of ties together our notion of codimension. And I think once we get into Harris and Eisenbud, we are guaranteed irreducibility as part of our varieties. So, although I've only started reading the first few chapters of that recently, and I have yet to strongly work through exercises, that's kind of the point of this, and so we shall see. Um, yeah. There's some stuff that gets into like some arithmetic geometry here. Um, but I don't know if we need that. Um, yeah, do we need semi-continuity? Hold on. Define a function by taking dim xp f from x to r is upper semi-continuous if for each x and r f inverse of the left ray is open. Okay. And then semi-continuity comes into play. The rank of a matrix of functions is semi-continuous. Dimension of a variety at a point is semi-continuous. Fiber dimension, rank of a finite type quasi-coherent sheaf, rank of cohomology groups of coherent sheaves in proper flat families. Uh, okay. Suppose P is a closed point of a locally finite type K scheme. X, show that the following three integers are the same. The X dimension of P, the dimension of the local ring at P, and the codimension of P. Yeah, these should all be either 0 or 1. Yeah, that makes sense. Okay. Um, suppose that X is a locally finite type K scheme of pure dimension n. K over K is a field extension, not necessarily algebraic. XK has pure dimension n. Okay, yeah, that comes from our earlier thing. That's not like... Oh, I guess that was for algebraic. Okay. But then in the non-algebraic case, like, what are we adding? Nothing. That's the point. Okay. Yeah, I don't think that that's super important. Enlightening strenuous exercise. Oh, God. Most surfaces in 3 space of degree d greater than 3 have no lines. Okay, well, this is where we hit some intersection theory. Projective, what? The most degree d surfaces in P3 contain no lines. Most means all closed points of a Zariski open subset of the parameter space for degree d homogeneous polynomials and 4 variables, all up to scalars. As there are d plus 3 choose 3 monomials, the degree d hypersurfaces are parameterized by projective d plus 3 choose 3 minus 1 space. Hint, construct an incidence correspondence from lines on the Grassmannian with cycles in projective d plus 3 choose 3 minus 1 space, such that the lines on the Grassmannian are contained on the open set, parameterizing lines contained in a hypersurface. Define a closed subscheme that makes this notion precise. Show that X is a projective d plus 3 choose 3 minus 1 minus d plus 1 bundle over the Grassmannian 1, 3. Okay, this seems like something that maybe is worth proving later. I'm gonna actually flag this in my book. Do later. I think if I try it right now, I will be overwhelmed and do badly. Okay, so Kroll's theorems is the next section. If I do end up doing this problem, it seems like a base change diagram type like problem in terms of difficulty. So if I do this problem, I'll probably record it. Might not be entirely correct, but yeah, so we can talk about Kroll's principal ideal theorem. Okay. Yeah, this section was very important. And then the next section is not super crazy. So yeah, I think we're good. Okay, so nope. Need that to be a different color. Rules. Oh, one extra L. Kroll's theorems. Um, okay. So we're going to state the principal ideal theorem in three different lights. One is the regular way, which is in a vector space, a single linear equation always cuts out a subspace of codimension 0 or 1. Codimension 0 occurs only when the equation is 0. And then the geometric version is that suppose X is a locally Noetherian scheme. And F is a function. The irreducible components of the vanishing of F are codim 0 or 1. And then finally, the algebraic version of this is that let A be a Noetherian ring, let F in A, then every minimal prime P containing F has codimension at most 1. If F is not a 0 divisor, then every prime P containing F has codim precisely 1. And that's actually a very strong condition. For example, locally principal closed subschemes have codimension 0, 1, and effective Cartier divisors have pure codimension 1. Here's another example, which you could certainly prove directly without the PIT. Okay. All right, so kind of an example of how to use this, where this becomes relevant to us, is an irreducible homogeneous polynomial in n+1 variables over a field K describes an integral scheme of dimension n-1 in projective n space over K. Okay. So, yeah. and the kind of key point here is this is dimension, not codimension, right? Um, because it's vanishing, right? Like the integral scheme here is the vanishing of this polynomial. And that is going to be dimension n minus 1. Okay. Um, okay. Um, let's see. Okay. Um, so definition, symbolic power. So let phi be from a ring A to A localized to Q. Define Q to the N to be phi inverse of Q to the N AQ. This is called the nth symbolic power of Q. And I'm assuming here that yeah, phi inverse QAQ or Q to N AQ. I'm trying to figure out exactly what this is. So let's go through the remark. This is a descending sequence of ideals of A. If and these are prime ideals, and Q to the N is a prime ideal. So yeah, I guess so. Q is an A is an ideal, and the symbolic power of the ideal is yeah, the coset, the left coset. Okay. Now the radical ideal of F is the intersection of the minimal prime ideals containing F, which is precisely a maximal ideal. So in the local ring, A mod the ideal generated by F, the no radical ideal is the maximal ideal. And so any descending chain of ideals eventually stabilizes. Oh my gosh. This is the p-adic numbers. So this is the other series that I'm about to start putting on my channel. I'm writing an honors thesis on p-adic analysis for my analysis 2 class. And so I've been working through KTalk, and I just finished, and that's been great. But now I want to go through, I think it's Elaine Robert. Anyway, Dr. Roberts' book, I think. I have it right here. Yeah, Dr. Roberts' book. On it, because that book starts a little bit further ahead, and I think that it'll just kind of add more to what I'm writing. But yeah, this is Hensel's lemma that Vikio goes through here. I don't know how important symbolic powers are for what we're about to do, but we'll see, right? Um, okay, so now we're about to have a bunch of important theorems. Um, let K be a field, possibly finite. Let N in Z plus. Let P1 through PM in projective N space over K be a collection of points, not necessarily closed. Then there exists a non-empty hypersurface not containing any of the PI. And this proof is by induction. So you assume it for M things, you show it for M plus 1 things. And really you can avoid finitely many points. This is kind of, I'm guessing, related to the ideal of to the idea of rational geometry, really. Okay, important exercise to be used repeatedly. This is a cool argument. Wow, okay. Well, if Vakil says it's a cool argument, it's gonna be a cool argument, right? Okay. The cool argument theorem. Okay. So 1. Hypersurfaces meet everything of dimension 1, or at least 1. In projective space. 2. Let X to included to PNK be closed of dimension R. Recently, I've been getting a lot of hate for my R's, so I'm trying to make them better. Then any codimension R. Wow, I feel like that's just worse. Any codimension R linear space meets X. That feels reasonable. Then there exists an intersection of R plus 1 non-empty. I'm going to abbreviate hypersurfaces as HS. Missing X. So the key step is there's a hypersurface of sufficiently high degree that doesn't contain any generic point of X. If K is infinite, show that there's a codimension R plus 1 linear subspace missing X. Okay, wait, hold on. Yeah. And then if K is infinite, there exists an intersection of R hyperplanes meeting X in a finite number of points. Give me just 1 second. I need to respond to a text. Okay. Um, Proposition. Proof. Prime avoidance. Okay. Sorry. Okay. Bound on codimension of intersections in affine n space. X and Y are irreducible closed, possibly singular of codimension m and n. Every component of their intersection has codimension. Oof. Then show that the Seeger embedding is a regular embedding of codimension D. Okay. This is actually very important. Maybe this is what I start tomorrow with, actually. Maybe I start tomorrow with this one. Okay, hold on. I'm going to write a list of things to start tomorrow with. So, start lecture 2 with, I need 12.3F and G. And then I also want 12.2.18. No, 12.2.9. Okay. There we go. All right, a useful characterization of unique factorization domains. Suppose that A is an Noetherian integral domain. A is a UFD if and only if all codimension 1 primes are principal. Yeah, I don't know. We don't really need that one. Okay, Kroll's principal ideal theorem can be used inductively. So if we have a strict chain of prime ideals, then there exist finite filtrations. Okay. Yeah, I don't think that's super important. I mean, like it is, but it isn't. Okay. I am kind of rushing to get to sleep. I have jiu-jitsu in the morning at 4, so that's gonna be rough. So Kroll's height theorem. So let X be an affine open where A is Noetherian. Let Z, a cycle, be contained in the vanishing of F1 through FR, be an irreducible closed subset where F1 through FR are in A. Then the codimension of Z is less than or equal to R. I can't write an R. Oh my gosh. Okay, I'm just writing it like that. Yeah, anybody who knows me at school knows that like I TA abstract algebra and I walked in and I knew like maybe a third of the class, maybe half the class. I walk in, I write up, office hours, right, with like the little R. And then I wrote a capital R elsewhere, and immediately people started just like, your R's are terrible. And anyway, I don't know. People are haters. Uh, yeah. So anyway, back to this. This is when we talk about height. This is height. Um. Yeah. So the proof sketch is that we have two cases. Um. So the local ring is Noetherian. And then this is the vanishing of M. And then we use the induction lemma for F1 through FR. Um, use induction on the principal ideal theorem. And so we take finite filtration, and yeah, then we get codimension less than or equal to R. Um, and actually, this is the only case. Yeah. That actually isn't too bad. That's definitely something where I feel like whoever's watching this can work it out, and I feel like I can work it out without doing it on camera. Maybe I'll go over it, maybe I won't. Um, like I said, this is kind of a selfish lecture series, video series. So if it's not super high quality, I'm really sorry, but this is very selfish of me. Um, yeah. D equals dim A. Yeah. Hmm. Okay, so given a oh, give me one moment. Okay, sorry about that. Geometric translation. Given a d-dimensional germ of a reasonable space around a point P, P can be cut out set theoretically by D equations, and we always need at least D equations, where D is the dimension of A. So these D elements of A are called a system of parameters at P. And I think the linear way of thinking about this um, is that if you have kind of a point of intersection of things, you need the dimension of the vector space, number of like pivots. Right? I was just explaining this to one of my students in linear algebra that I TA earlier today. He was asking me, like how do you know how many solutions you have? And well, the answer is basically the dimension of the column space of the matrix. But of course, for nonlinear equations, it holds kind of similarly. So theorem, if dim A equals D, then P, this point P in, I think, A, yeah, P in A is cut out by at least the equations. Yeah. And so then these D elements of A are a system of parameters. Um, so these polynomials are a system of parameters. Okay, I really want to finish this off. There's just kind of some small things going on. But it ends with this really nice geometric application of Kroll's principal ideal theorem. Maybe that's what I'll start with. I'll start tomorrow with finishing off this, and then I'll do Kroll's principal ideal theorem applied to lines on hypersurfaces, 12.3.14. Yeah, that'll be good. And this will extend 12.2.18, 12.2.18. Where? Oh, lines on hypersurface part 1, which was the 12.2.n. Yeah, so it makes sense, I think, actually, to end here and then start tomorrow with these two. And then, yeah, we'll finish off tomorrow. We'll finish off 12.4, which is dimensions of fibers, morphisms of varieties, which should not be terrible. Then we'll get into tangent spaces, lines on varieties, which I think is a really cool topic, because at the joint meetings this year, Dr. Koyar from Princeton gave a wonderful talk on this topic, and so now I'm actually going to get to see some of it firsthand. And then we'll get as far through that and some examples there as we can. Yeah, Bertini's theorem, definitely valuable. Maybe we'll end tomorrow with discrete evaluation rings. Start of discrete evaluation rings, at least. Because that sets us up for divisors. And then the next day we can get into 13 and 4. Well, 13 and then 14.1. No, we need 14.2. Wow, this is such a well-written book. Gosh, this is such a well-written book. Okay. Enough fangirling. This has been a great first lecture. I hope this wasn't too hand-wavy. If it was, I'm sorry. We'll pick up tomorrow with some practical examples. Thank you.